This is a solution for the question from text test 4 on page 496. It's question 3. So they start off by giving us a rule, which is the temperature of the milk, which was heated up to 45 degrees Celsius. As it cools, as time passes, the temperature is calculated using this formula, 15 plus 30 times 10 to the minus 0.02 T. And they say in the question that the initial temperature is 45 degrees, and let's just verify that by calculating with this formula. And I'm just going to call this first calculation T0, which is just the temperature after 0 minutes. So if I was to work that out, clearly I'm going to end up with a power of 0 up here, and a power of 0 on that 10 is going to end up giving me a value of 1, and that calculation works out as 45, which was the initial heat of the milk. Now, they had already told me that in the question, I'm just verifying that. And so that's my solution for part 1 of the question. So now I can only give the milk to the baby when it's gotten down to 35 degrees, so I want to know how long it'll take that to happen. So I simply let 35 equal to the formula they've given me, and then I want to evaluate T. So I'll start bringing the 15 across, and really to get at this T value, what I need to do is I need to isolate the value that has the T as its power. Now it's very tempting to stick in a log on both sides here, but actually 30 and the 10 need to be treated separately. So it's this part of the term that I need to actually isolate. So I'll just bring the 30 across and divide it. Okay, and now I want to get in at that T. So to get in at that T, I'd like to basically get rid of the 10 here, and I can do that by applying a log base 10 on both sides of the equation. And you'll just notice there that I've cancelled down 20 over 30 to 2 over 3. Now what this log to the base 10 will allow me to do over here is it'll allow me to eliminate the log to the base 10 and the 10. They effectively cancel out. Again, just to explain why that happens, remember that I can use my rules of logs to bring the power in front of that log. So I'm bringing down that minus 0.02 T, and then of course this is resolving into a value of 1, and when that's multiplied by minus 0.02 T, I'm just left with minus 0.02 T. And now I want to work out the T, so I'll get it by itself. So I'll bring the minus 0.02 across and divide it, and then I'll stick the whole thing straight into my calculator. I mean, you could work out the log to the base 10, 2 over 3 first of all, and then divide it, but what's the point? You'd be having to round off and then calculate again. So it's better off actually here just to type the whole thing in one go. So I'd need to leave the milk for 8.805 minutes. And they haven't specified in the question how they want this rounded off, so I'm just going to leave it as that. Obviously, if they asked for it to the nearest minute, you could round it off to 9 minutes. Okay, so part 3 then says use the rule to find the room temperature. So let's just think about what happens with the bottle of milk. So the bottle of milk gets heated up, and then imagine that I perish the thought, forget to feed the baby, and the bottle of milk just ends up sitting on the counter for ages and ages and ages and ages. Obviously, it's going to cool down. Now, it's not going to cool down to freezing. You know, there's a limit for where it's going to cool down to, and the limit that it's going to cool down to is the temperature of the surrounding room, the surrounding air. So if we basically work on the basis that we've left the bottle for ages, and then we work out the temperature after a really long time, that should give us a good value for our room temperature. So here's my rule. So what I'm going to do first of all is I'm going to just take an arbitrary value for T and see what I think the answer should work out as. And then I'm just going to have a quick discussion about what's actually happening with the power as T increases and what effect that's having on the rest of the calculation. So I'm going to start by saying that I leave the bottle sitting on the counter for, I don't know, we'll say 100 minutes, okay? Because I kind of reckon after 100 minutes it's probably cooled down to room temperature. Well, now I can just substitute this 100 in and evaluate T. And so when I work this out then, I'm going to get an answer of 15.3 degrees Celsius. Now, this 15 clearly came from that 15. So I've definitely got the 15. And this 0.3 here came from this part of the formula that can change depending on the value of T. So what's after happening? As my T gets bigger, this value gets smaller and smaller. It might make it easier to visualize what's happening here if we were to write our formula in a slightly different way. So I can write my formula, instead of writing it in this format, 15 plus 30 times 10 to the power of minus 0.02 T, I can bring the 10 underneath the 30 and write it as 10 to the power of 0.02 T down here instead. Now, as my T gets bigger and bigger, as more and more time passes and the poor baby is left to starve, the value of this 10 to the power, well, the value of the T is going to go up, so the value of the 10 to the power is also going to increase. So I'm dividing 30 by bigger and bigger numbers, And eventually, after an infinite, if you like, amount of time, I'm basically going to have 30 over 10 to the power of infinity. So a number divided by a really, really large number approaches 0. And so a better calculation really for room temperature would be to say that it's actually equal to 15 degrees.